Hello, and welcome to the Scientific Adventures of Beardman. Today we're going to be looking at a skill on positivephysics.org in Unit 20 Circuit Analysis titled Various. There's a video that Jack Replinger put together, and that's great. But I wanted to create one that uses a slightly different method of calculating. In case you've been following along in physics classroom, you learned a way of dealing with electric potential called Know Your Potential. And I wanted to connect those two things together here. So let's go ahead and jump right into an example. I want to actually, really quick, I am going to link right here, or maybe I've already done it, the physics classroom video that I made on knowing your potential. So if you didn't do that, you could go there and take a look at that method. I'm going to assume you've already seen that video. You already know how to use that method to figure out electric potential difference. So let's start out here by talking about our voltage. Okay, you could do either first, either the voltage column or the current column. We're going to start with voltage. So we're going to create our colors here. We always put blue by the negative side of the battery and color the wire there blue, meaning it's got zero electrical potential. Okay, and then the battery pumps up the current, so now it's got a lot of energy. We can see here that the source is going to make it 220, so the electric potential here is 220. Now remember, this voltage here is electric potential difference. Okay, so that means that going from one side of the battery to the other means you're going to change by 220, or there's a difference of 220 volts. Okay, let's look really quickly at that definition in case you've been confused by that definition. So electric potential is the amount of energy each coulomb of electrons has, or each coulomb of charge has at a given point compared to a reference frame. So our reference frame is the negative side of the battery. So compared to the negative side of the battery, the positive side of the battery has 220 volts. I should have put volts there. Let's do that. Volts. All right, so what is electric potential difference? Well, voltage or electric potential difference, notice I kind of yelled at you here. Sorry about that. If you're up with online lingo, all caps means yelling, but I wanted to point it out, and I can't change the size in this particular, in a Jamboard like this very easily. So the difference, so voltage is the difference in electric potential between 2 points. The 2 points are often either side of a battery or on either side of the light bulb or other generic resistor. Okay, so the two sides of the battery, the two sides of a generic resistor, or maybe these are light bulbs, you get the idea. Okay, so then we would next go ahead and mark this orange, and we don't have orange, so I'm going to combine red and yellow, okay, to make orange. And then we've got yellow over here. And then finally, it drops to green down here. Okay, all those wires. Remember, any wires that are connected are the same color. Okay, and then from our table here, we see that A is going to change there's going to be a electrical potential difference of 50. I'm going to write those in black here. So across A, we're going to be losing 50 volts. That 50 volts isn't being lost. Remember, it's turning into light and heat, or whatever this resistor is doing, probably light and heat, or at least heat. Then we see that we've got D at 30. So let's go ahead and draw that in. As it goes from yellow to green, it's going to lose 30 volts across D there. And finally, we have F at 100. So over here at F, we see the energy changing by 100 volts. And remember, when I say energy, I mean energy per coulomb. Okay, energy per coulomb. So then we want to take a look at the rest of these. So what does that mean? Well, if we are at 220 and we lose 50, well, that means as we get to orange here, we're now going to be at 1 oops, let's use the marker size, at 170 volts. Okay, and let's do it in yellow so it looks kind of orange. 170 volts. Okay. So then, and then also we down here, we know that this is 100. So if it ends up at 0, it has to start at something. That something minus 100 gives us 0. Well, that will simply be 100. So this whole green area is at an electric potential of 100. And so when it goes from an electric potential of 100 to an electric potential of 0, that means the voltage is 100. Okay, so then we can look up here. We see that we're going from orange to green. Well, to go from 170 to 100 means that we would lose 70 volts. So then we can plug in C would be 70 volts. Okay, now the only thing we have left is to figure out what this yellow section is up here. Well, we know that through D, it's going to lose 30, and it's going to end up at 100, an electric potential of 100. And so what would lose 30 to end up at 100? That would be 130. Okay, so 130 volts of electric potential would lose 30 to end up at 100. So now we can figure out the two that we've got left. So we could do E first, we could do either one. So this is going to go from 130 to 100. Okay, so that will be 30 volts. Hey, I fit it on. And then over here, B is going to go from 170 to 130. So that means it loses 40 volts. Okay? All right. So, let me write these in. B was 40 volts. Volts is at the top. I don't have to write it down here. And this one was 30 volts. Okay, which we got here and here. All right. Next, I wanted to show you how I like to think of current. Okay. So this is a lazy river. Okay. The water flows through it, right? And you flow through on these tubes, and there might be some places where it splits up, and then places where it comes back together. Okay. But if you look at any point here, and then another point over here, however many gallons are flowing through here every minute, have to flow through here every minute. Because if more were flowing through here, we'd get this big pile of water here, and that doesn't happen. The same way gravity keeps this all at the same level, electrical fields do that in wires in a circuit. Okay, so the current at any one point here has to be equal until we get to a split. When we get to a split, if we had, let's just come up with some numbers here. If we had 100 gallons flowing through here each minute, well, then maybe we'd have 60 gallons flow this direction every minute and 40 gallons flow here every minute. Okay, because we can't just create more gallons. So these 100 gallons have to do something, and maybe 40 go one way and 60 go the other. Well, in our case, we're not measuring gallons of water. Instead, we're measuring current. We're measuring the amount of charge that flows through a point at each moment. So the I over here might be 100 amps. The I over here might be 40 amps, and the I here be 60 amps. The key, of course, being, if you didn't catch it, is that the two paths here have to add up to this path. If 60 goes that way, what's left over? 40 to go that way. So let's take a look at what's happening in our circuit here. Okay, so let's go ahead and erase our voltage. Okay, you can always go back and pause and take a look at this if you want to see all these beautiful colors. Okay. And there we go. All right. So now if we take a look at the current going through here, we know that there is 1.2 amps of current going through here. Since there's nowhere for it to split off, this must also be 1.2 amps. So we can put in 1.2 amps there. But here it's going to split, okay? And so we know from what we see here, we see that C has 0.5 going through it. So if we have 0.5 amps go that way, well, if we had 1.2 amps go this way and 0.5 of it went that way, what's left over to go there? Well, that would be 0.7 amps, okay? Because 0.5 and 0.7 is where our 1.2 went. 0.7 that way, 0.5 that way. So we can jot that in here. B is going to have 0.7 amps through it. Then we can see that 0.4 split off to go this direction. So how much must go straight? Well, if we had 0.7 coming into this junction and 0.4 went that way, that means we had to have 0.3 amps go this way. Okay, and if 0.3 amps are going that way, that means we're having 0.3 go through E. Then finally, our 0.5 amps from here, our 0.4 amps from here, and our 0.3 amps from here all combine back together to give us 1.2 amps, 0.5 plus 0.4 plus 0.3, which is going through F, which, by the way, it's really good that that matches up because that must equal what we have over here because there's no more splits in between here and here. All right. The last thing I want to do is point out another way of looking at electric potential. Okay. So, and that uses our little system here. So electrons or charges in a circuit can be thought of in terms of their electric potential energy. Well, we studied a while ago gravitational potential energy. Okay. And so here might have 120 joules of gravitational potential energy, depending on how much water is there and so forth. Down here at our base would be 0. That's our frame of reference. That's where 0 joules is. And then at each other point here, we might have a different amount of energy. Okay? Well, the same idea is going on here in electric circuits. Your battery, there's a water pump here that pumps water from 0 up to 120. That's like your battery. It's pumping up the electrons so they now have more energy. As they fall down, they lose energy. Here, that makes sound. It probably heats up the water a little bit. In the case of a circuit, it's probably lighting up a light bulb, for example. So as the water or electrons lose energy, they're giving that energy to make light. And then they'll flow through the wire where everything's the same energy. Okay, so all this, the wires are the same energy. This is like the wire because we pretend wires have 0 resistance at this level. Okay, same thing here. Going from here to here, there's essentially 0 difference, and so the water just kind of flows. Okay, and then we have different drops. Now, I want you to notice, no matter what happens here, no matter which route this takes to get down to 0, it's going to lose 120 joules of energy. Now, keep in mind, we now talk about joules per coulomb. And so remember, joules per coulomb is a volt. Okay, so we'd be talking volts in an electric circuit. But if we have 120 over here, then we would lose 120 no matter which way we went. So we could add up the amount we lose each time. We lose 20 there, we lose 10 there, we lose 5 there, we lose 10 there. Okay, and all of it has to add up to 120 because all the water ends up down here at the pool. So if we want to use that method, which is similar to what Jack Recklinger does in his video, we can look at this and say, hey, we're going to have to lose 220 total. Okay, let's write in all the ones we know. Okay, this is just another way of thinking of it. Okay, so we gain 220 here in our pump, in our electric battery. And so if we lose 50 here and 100 here and 30 here, we look for paths where there's only one thing we don't know. Because remember, every path has to lose, I wrote the wrong number here. Every path has to lose 220 volts. Okay, so this path, we lose 50, we lose something, and we lose 100. So we've lost 150. How much left do we have to lose to get to 220? And that would be 70. Okay, because 50 plus 70 plus 100 gives us 220. So C must be 70. Okay. Then we could look at our next path. We could look at this path, 50 plus something plus 30 plus 100. Okay, so we had a 50 plus 100 plus 50, 150 plus 30 is 180. So what does this have to be to get us to 220? That would have to be 40. So we'd lose 40 total, or 40 going across B, so that we're sure we lost 220 through the whole thing. Our final path here that we've got is 50, 40, something, and 100. So 50 plus 40 is 90, plus 100 is 190. We need to get to 220. That means E here must be 30 volts. Okay? All righty. Hope you learned a lot here. And as you puzzle through these problems on positive physics, you have success. If you have any questions, ask them in the comments below. Be sure to click that like and subscribe button, and we'll see you the next time on Scientific Adventures of Beardman.